The next talk will be by Ernie Ostuno from Grand Rapids, Michigan. He'll be discussing estimating wind speeds from tree damage. Go ahead, Ernie.
All right, thank you. And this kind of falls into the category of successional planning that Mike talked about there. Basically, this is a long career worth of storm surveying stuff that I've learned over the years, and that we're training the younger meteorologists in our office to take over in years to come for future storm events. So I got a lot of slides. I'll try to go through it quickly but effectively. The first photo you see there is kind of a typical windstorm that we get. This is a small tornado. And the one thing I want you to notice there is, you got a big tree that's taken down, a lot of other big trees snapped in the background, but you'll see those younger trees, they're still standing. And that's kind of the typical way that forests evolve. The wind selectively takes down some of the bigger trees, and then the trees that are basically waiting for that to happen, the younger trees, suddenly have a lot of sunlight and they'll grow quickly, and the forest will regenerate. So that's an illustrative photo. But if we get down to the original tree, the first thing we look at for failure, it's kind of analogous to buildings. With buildings, we look for the failure points and try to figure out what the wind speed was responsible for causing the failure. We do the same thing with trees. And we think of trees as three main parts. One is the mast, that's the trunk. The anchor, that's the root system. And then the crown of the tree is what we'll think of as the sail. So that's going to be taking the brunt of the force of the wind. Trees can fail at any of those points, whichever is currently the weakest. And so we'll look at the failure points and try to estimate the wind speed that caused that failure. So these three photos at the bottom here are interesting examples of how trees survive catastrophic wind events, wind events that'll take out most of the trees in the forest. So the mechanisms that trees develop to deal with extreme wind: swaying or flexure. That's the old bend, don't break strategy. And then crown architecture, that's adaptive to the conditions the tree is growing in. Streamlining of the crown and limb shedding, those are two very important concepts. We'll look at those in more detail. And that's the way the tree differs from a building. You can actually reduce its surface area and thus reduce the force of the wind for a point. And we'll talk more about that, how that evolves as the winds increase. And the tolerating extreme wind also depends on the tree's previous damage or disease, and also the stand history if it's part of a forest area. So we'll look at those issues too. But the three photos, that's basically, two of them are the result of limb shedding. And both of those trees, without having the trunk snapped or being uprooted, can regenerate foliage. And the photo of that spruce tree on the lower right is a tree that was sheared off during the tornado of 1956. I took this picture 60 years later, and there were probably two primary limbs that survived, and one of them turned vertical, and you can see a bend in the trunk. And this is typical all along the path of that tornado where there was forested areas. You see the same thing, this kind of S-shaped bend in the trunks of trees, and that's generally trees that were snapped off, but primary limbs survived, and one of them grew and formed a new trunk of the tree. So that's one of the strategies trees have adapted to survive extreme winds. So the first concept to look at in detail is crown streamlining. Again, this is very important. Buildings can't really do this. They can't reduce their surface area. And if you think about force of the wind, it increases exponentially a square of the function of the area being affected by the wind. So if the tree is able to have the crown branches bend laterally with increasing wind, it's going to effectively reduce the crown area exposed to the wind, and thus the drag force on the tree, on the root system, and on the trunk itself. So some species, it could reduce the frontal area of the tree by 80%. So it's kind of remarkable. That's a great reduction in the amount of force being applied by the wind. Once it becomes maxed out, then you'll start to see that large exponential increase in the force, and that's when trees will start to go down en masse. That usually happens, coincidentally, right around the border of EF0 and EF1 for a lot of species that we find in the Midwest and Eastern United States. And even shape of the leaves and size of the leaves can actually effectively reduce the drag coefficient for some species. Limb shedding is another way that trees will survive strong winds. And if you look at some of those tree species, there's some examples there: black ash, cottonwood, and basswood. Those three species with brittle wood for the limbs, they'll do a lot of limb shedding. They'll lose much of their crown, but the trunk and the roots will survive, and the tree will survive. And those trees can get very large, especially cottonwoods in the upper Midwest. The other thing we look at is site conditions, where you have like a high water table or there's bedrock close to the surface. You're not going to get deep root systems. They're going to be very shallow, and then they're going to be prone to uprooting. And that's commonly what we see in Michigan, where there's a high water table. We'll see a lot of shallow rooted trees come down in strong winds. Also, if the soil is locally wet, this year we're one of the wettest years on record so far, so a very wet soil, you'll typically see more uprooting, although it is rare with deeper root systems, quite common with intermediate or shallow roots. The big thing that we don't think about a lot, but we do see it a lot when we go out on surveys, is in residential areas where trees have been planted, suburban and urban areas, you'll see unstable root systems. A lot of time this is because the tree was planted too deep, so the roots will actually wrap around the trunk and cause failure right at the ground level. So when you see that, look for the telltale signs of constricting roots, what we call stem girdling roots around the trunk of the tree. That's a common failure point. The other thing we notice in red pine plantations back during the Depression, the Civilian Conservation Corps planted many thousands of acres of red pine over land that had been clear cut during the late 19th, early 20th century to reclaim that land. Those trees are pretty brittle. They're very prone to snapping at winds, probably in the EF0 range. Another important variable to look at is height diameter ratio. The diameter of a tree is measured about 4 feet above the ground. Take the circumference and then you divide it by 3.14 to get the diameter. And we call that DBH, diameter at breast height. That's a forestry term. So the typical tree, especially open grown, is about 20 to 30 to 1. But if you look at forest examples where trees are competing with each other for sunlight, they'll generally grow tall and thin. So you could get 50, 60 to 1 height diameter ratios. And once you're up in that range of 60 and higher, that tree becomes susceptible, especially if other trees around it are thinned by either people or wind disturbance. So you'll see failures of those. You can see that little picture there, the profile of the tree with the tall, skinny appearance. That is a high height diameter ratio. That's going to be less tolerant than those spire-formed conifers there in the understory. The other thing we look at, again, that would cause failure of the tree at winds probably 60 to 70 miles an hour with these tall height diameter ratios is the live crown ratio. So if you have a high, or what we call a low live crown ratio, where you have a high crown and a tall spindly trunk, that is going to put a lot of force on the trunk, especially higher up on the trunk, and it could snap the tree fairly easily. And then if you look at those conifers, again, they're going to have a high crown ratio, and those could be prone to being uprooted if they're fully exposed to wind. If we look at stand dynamics and forest development, usually most of the windstorms we get in that introductory photo I showed, you'll get swaths or sections that are blown down, and you'll see generally what's left behind is the understory and a few of the canopy trees, and that's typical of most of the wind disturbance that we get from derechos that are usually in the say 70 to 90 mile an hour wind range. So the understory in that case is going to be getting a lot more sunlight, and it'll be growing up into what becomes a mixed aged forest. So we start out in the upper left there, the stand initiation. So you have either forest succession or a complete blowdown. So these saplings or younger trees will start growing. They will take up all available sunlight eventually when they grow tall enough. And that's the stem exclusion stage, where there's no more room. The canopies are filling up all the areas of getting sunlight. So you just have a few of the shade tolerant species growing in the understory. And then the demographic transition at the lower right there, that's when you start to get some wind disturbance or selective cutting or any other type of disturbance. And then you'll start to generate some of the understory trees into the canopy. And if you get a very destructive derecho or wind event, tornado that comes through, you could end up right back at stand initiation stage. Otherwise, you'll evolve towards the multi-age stage, and that's usually the most wind-tolerant forest because the trees have basically survived plenty of windstorms. At some point, the older trees will become susceptible because of either insect disease or rot from advanced age. And like I said, most of the wind disturbance we get is just going to be swaths of trees or selective trees taken out. You very rarely get a completely stand initiation phase reinitiated because you don't get a large scale blowdown, say winds over 120, 30 miles an hour. That's pretty rare. That's going to be either your extreme derecho or your EF3 range tornado that's going to be able to do that to level an entire forest. So those, if you look at any small unit area, those events are going to be an order of magnitude less than your selective elimination of trees that would occur at lower wind speeds, say lower than 120 miles an hour. So if we go down to the lower range, less than 70 miles an hour, you start to see damage occurring probably around 55 to 60. Small limbs might come down, or rotten limbs will come down maybe about 45 to 50. But usually to see entire trees snapped, even some of the weaker ones, you'll get wind speeds generally in the 50 to 60 mile an hour range. Start seeing that. So you have the large rotted limbs. You get the rotted trunks, shallow rooted trees, and then the healthy trees are usually going to be weak because you'll have a high crown ratio, or you'll be at the edge of the forest, so more fully exposed to wind, and a high height diameter ratio as well. So you start to look for those things when you're looking at non-rotted trees that get snapped at that range, and then you look for shallow roots if trees are uprooted or very saturated soil conditions. As you move up towards EF1 range, high-end EF0, you'll start to see some of the lower tolerant wind species, especially red pine plantations, early successional species will start to go down. And one thing you notice here, even though you see a lot of trees down in these plots, if you look around the edges of where the trees are down, you'll see trees that are standing there. Those are usually hardwoods. They're usually going to be more wind tolerant because they are at the edge, so they're not as tall and skinny as the trees in the interior that are competing with each other for sunlight. So you'll have a lower live crown ratio, or a higher live crown ratio, and a lower height diameter ratio. So it'll be lower center of gravity in these trees, and more wind tolerant than the trees in the interior of the stand. Here's a really nice view of a red pine plantation. This was probably an EF0 tornado. It came through that stand of hardwoods with very little damage. There might be isolated trees down there, some large limbs down, but when it hit the red pine plantation, suddenly it's doing damage that looks like EF2, but the winds were still probably in the upper EF0 range, maybe low end EF1 there. And you could see what it did to those pine trees. Most of all of them were snapped. And here's the other end of that same swath of damage. And again, as soon as it crosses the road out of the red pine plantation, there's very little damage in the stand of hardwoods there. So this is typical what we see. And if you didn't know it at first, you look at the the drone footage or aerial footage, you say, wow, that's a pretty impressive EF2 swath of damage. But from the ground, you'll see that these are red pine plantations, and dramatic difference between them and different tree species surrounding them. So we're going to go up a little further here into the EF1 range, where we start to see structural damage, some roofing damage, probably at 100 miles an hour here, and the corresponding tree damage close to these, close to the structural damage. You could see the limb shedding, quite a bit of limb shedding. I believe those are sugar maples in the upper right. And almost all the small limbs are taken off, and a lot of the large limbs are taken off. But they didn't go very far. They were just stripped off. They broke off and landed near the tree. They weren't carried far away. This was an EF1 tornado. But we did see a lot of snapping and uprooting, and which corresponded, I feel like the EF scale corresponded with each other. So one of the things you want to do when you're out on a survey, obviously, see a lot of tree damage near structural damage, you want to reconcile any great differences you come across in the EF scale. Sometimes you'll see houses that weren't touched, didn't lose the shingling yet, all the trees are down, or you'll see, more unusual, you'll see structural damage, but the trees not significantly damaged. So you want to reconcile that and try to say, find out why the tree damage, the two different damage indicators do not line up with what you're getting for wind estimates from the EF scale. So some of the important findings based on forest wind disturbance research: wind speeds of 60 to 90 miles an hour. That's when streamlining is occurring of foliage and branches. So the force on the trees is not increasing exponentially at that point. It's more linearly with wind speed in that range. So you'll see big differences in damage between stands and species, and which we illustrated with the drone footage of that red pine plantation. Now, once you get up in solid EF1 range, streamlining becomes maxed out. Force on the tree increases as an exponential function of wind speed, and so you're going to see a lot more trees coming down. Basically, as the wind is increasing exponentially, the force is. And then once you get 120 plus miles an hour, into the solid EF2 range, you're looking at most of the forest being leveled. Again, just the seedlings and saplings. And so you're back to forest initiation stage. And you'll see a lot less difference between stand type and species, because almost everything has been either snapped or uprooted. So to get a little more specific, this is rules of thumb that I came up with over the last 30 years of surveying in Michigan and Pennsylvania. Wind speeds of 45 to 64 miles an hour, you're going to see shedding of small and or rotted limbs. A few weak and or rotted trees with shallow roots will be snapped, uprooted. As you get into the severe range, EF0 range, shedding of large healthy limbs, and that's again the limb shedding when the streamlining is maxed out. And a few healthy trees with deeper roots snapped or uprooted. So that's EF0 range. And then once you're up into the EF1 range, again, the streamlining becomes maxed out. Limb shedding is common to almost all tree species. And you're getting an exponential increase in the wind force with a large increase in the percentage of snapped or uprooted trees in that range. This is from forestry study of the derecho across northern Minnesota, the Boundary Water Canoe area in July of 1999. And this is similar to other studies. You look at the wind tolerant species, you see an increase with mortality as there's an increase in tree size. You see the same thing even with the less wind tolerant species. There's an increase in mortality with size. And then the group that increases the most in terms of mortality with trunk diameter, again, we're talking measure the diameter of the tree about 4 feet above the ground. And that's kind of a way to get a quick look at larger trees versus smaller trees with less of a wind profile. But it doesn't say anything about actual height diameter ratio. You can infer some things from it, but not all things. So usually the species that are in group 2 that you see a large increase in mortality with an increase in size of the tree are going to be the what we call spire-form conifers. Those are going to be your spruce trees, your balsam fir, those type of trees, or old trees prone to rot or disease. So if we look at the species breakdown, this is a separate study, but kind of showing the same thing. July 1995 derecho, and these were 2 high-end derechos with the max wind speeds probably 100 miles an hour or so. And you break it down by species, you'll see that the hemlock and beech were the tree species that we saw greatly increasing mortality with size, and usually that's going to be an indicator of tree age for those species, and the older the trees are going to be more prone not only to being exposed to more force of the wind because they're larger trees, but also have issues with rot and disease and insect damage for beech especially. So all other factors being equal, wind tolerance decreases with increasing tree size. Deciduous trees, and this is common sense here, wind tolerance is going to decrease when they're leafed out because there's going to be more drag than if the trees were not leafed out. So early successional species, less wind tolerant, those are the ones that are going to grow fast and have tall, spindly trunks and smaller crowns, and then a good strong wind will snap the trunk more easily than the late successional species that generally are going to survive windstorms to get to the late successional stage. Center of gravity is important. Low center of gravity explains why open grown edge trees are more wind tolerant. We saw in that photo of the trees that were leveled in the interior part, and the edge trees survived. Crown architecture is important. Small crown at the top, that's your live crown ratio, is generally less wind tolerant than other growth forms. So now I want to turn quickly to look at individual species. And the interesting thing you'll notice here, if you look at the weak species, when you go down there, there's a couple species of oak that are included that are fairly low wind tolerance, water oak and pin oak. And then if you look at the list of strong species, you'll see that there's a couple species of oak, bur oak and live oak, that are very wind tolerant. Bur oak being in the southern plains, they've survived tornadoes in Oklahoma, probably in the EF2 range, or even maybe even higher. So they're a very wind tolerant species. So oak as a species varies quite a bit. Why do I mention that? Well, if we look at the current damage indicators for trees in the EF scale, DI is 27 and 28. They're split up between hardwoods and softwoods, and oaks are lumped into hardwoods, which are generally thought to be more wind tolerant than softwoods. So there's some issues with the EF scale. Another one is your degree of damage, number 3 and 4, trees uprooted or snapped. We don't have any real data suggesting that that is true. Generally, it's believed through studies that have done by the forestry community that there's not a whole lot of difference, force necessary to either snap or uproot a tree, generally speaking. The other issue is trees debarked. Debarking could occur at fairly, we've seen it, I think, at EF2. There are some cases of debarking at EF2. And basically what it comes down to is the tree species and debris hitting it. Large sheets of bark could come off a tree if it's being pelted with debris. Usually when you have clouds of debris that do that kind of thing, you are up there in the EF4, EF5 range, but it could occur to some species of trees, even down at EF2 range. So looking at summarizing that discussion, there's no real reason to separate hardwoods and softwoods or snapping and uprooting. Instead, we should consider the variables of tree size and species, improper planting, and a lot of other stuff that the forestry community has found through many field studies. So again, debarking is more of a function of flying debris and species and could occur over a wide range of wind speeds. And also looking at stands of trees rather than individual trees. So instead of the old damage indicator, we have American Society of Civil Engineers wind speed estimation in tornadoes working group number 5 is looking at trees as a damage indicator. There's other working groups looking at various other issues with the EF scale and coming up with a standard through ASCII, a wind standard for damage to buildings and other damage indicators, including trees. So here's some of the people, and a lot of the work I've cited was done by these people: Chris Peterson, University of Georgia. I also worked in the past with Lee Frelich, University of Minnesota. You see Chris Godfrey, North Carolina at Asheville, Chris Capella, Dave Sills, Environment Canada, John Gordon of the Weather Service, William Fountain, University of Kentucky. A lot of people are working on various aspects of creating models of tree fall patterns. There's 3 separate models that will assign wind speeds based on tree fall patterns in tornadoes. And this is especially useful in the southeast United States, where there's large areas of forest area like the Smoky Mountains. And but it even can be applied in suburban areas like Joplin, Missouri, for instance, in that tornado. A lot of the results were the tree fall pattern there was used to calibrate the tree fall models that are being developed. So instead of hardwoods and softwoods, we have a proposed single multiple tree DI. And these are going to be your typical strong and weak, and that will correspond to expected upper bound and lower bound from the EF scale. And if you look at the normal resistance, we're looking at leafed out deciduous trees, typical species, typical live crown and height diameter ratios, growing on well-drained soil, so not shallow rooted. And then the above normal resistance applied for deciduous trees that are leafless when we get the early tornadoes or winter tornadoes, so anywhere from February to March and April before the trees leaf out. Strong species of mature forest, high life crown ratio, low height diameter ratio, and then for the weak species, pretty much those even age monocultures and shallow or saturated soils. Yeah, and of course, the stem girdling roots or newly planted trees in the residential areas. So here's DI 27, single tree, and there's a sub DI A and B for tree size. So it's split up. There's not a huge amount of difference for tree size. The other thing you'll notice here is degree of damage 4 and 5 are identical. So those are probably going to be combined. We'll have to come up with a new degree of damage 5. And then you'll notice the debarking is not on there anymore, but we have put stubbing of limbs, where most of the limbs and large limbs have been removed. And bodily removal of the tree, as we have seen in some videos where the tree is actually snapped or uprooted and pulled out and carried, wafted through the air by the tornado. And then the multiple trees, this was adapted from Dave Sill's work with Environment Canada and the Canadian EF scale. So those are the numbers from there. We're still in the process of refining those numbers, but that's basically how we have it laid out to work on 2 damage indicators for trees, single tree and multiple tree. So that kind of wraps it up. There's a bibliography, some of the concepts, a lot of the concepts I went over are illustrated in those papers. And at this point, I guess we'll turn it over to questions.
Yes, great presentation, Ernie. If you have any questions, please raise your hand or put them in the chat. I'm not seeing anything yet. I just had a quick question. Sometimes it's like in the West, we have a prevailing wind and the trees are tuned to that type of wind, and then you have a wind coming in a different direction. Do you ever look at those situations? Do you have them in the Midwest?
Yeah, that question.
Yeah, go ahead.
And that question comes up a lot of times for large scale winds. We had a Hurricane Floyd, the remnants of Hurricane Floyd in 1999. Poconos had massive tree damage, and the theory was that it was made worse because the trees were not as tolerant to east winds as they were to west winds. I would like to see, some type of study done, like what the forestry people do. They do winching studies. I believe there are some publications, and I wasn't able to find one to include in this bibliography, because that question is a good question, and it has come up many times. Winching studies that would prove that, but you can infer it, I think, because we do see that even in Michigan. If we get a strong east wind or southeast wind, and that's usually a direction we don't get very strong winds from very often. So trees are more selectively taken down in those unusual directions. The other question, Dave Sills, I was talking about this with him a couple of days ago. That study that he did recently, and I say, oh yeah, it's the Mansour et al. 2020 right there. So if you go to that link, I believe that they mentioned differential direction in a tornado. So a tornado, you're going to get a quick blast of wind, but it's going to be from directions, again, that trees may not be adaptively capable of resisting as well as they would with wind direction from the prevailing wind direction that they've adaptively grown in during their lifetime. So that reference there might have some more information on that in relation to tornadoes, differential winds and tornadoes. But it is an interesting concept to think about, and it does make sense that a tree isn't, if it hasn't, typically been exposed to strong winds from a certain direction, it's going to be more susceptible than winds that it typically has been exposed to. And we do see this at, the edge dynamics of the forest. If you get stand of trees where, say, a power line goes through, and suddenly you have these tall, spindly trees that were competing with other trees. Now they're open to the wind. They're very susceptible to being snapped by strong winds, just because they haven't experienced strong winds from that direction before. So I would say yes, but I'm hesitant to really try to say how much of a factor it is, because I don't know of any studies that have quantified that answer to that question. And the only way to do that, think would be winching studies of a particular stand of trees. But just anecdotally, it's my experience that if we do get a strong easterly wind here in Michigan or back in Pennsylvania, it does seem like tree damage would be more severe than a similar event with a westerly wind speed.
Yeah, that definitely makes sense. We've had situations in the Colorado Rockies as well where that has happened, where we'd have a traditional westerly wind, but then you have a easterly wind develop at like a downslope and has caused blowdown events up in northern Colorado. So it definitely makes sense. I am not seeing any other questions, Ernie. So thanks again for a great talk, and thank you everyone for joining us. So that will end our talk.
Thank you.